this lecture, we're going to talk about numeration systems using other bases. What I mean by that is bases other than the base 10, which is the standard base that we use for all of our modern numbers. So before we can do that, we need to have a really good grasp on what exactly we mean by a base 10 number and what the individual parts, the individual digits within a base 10 number represent. So what we have here, right, my example 1402, the 2 represents the number of 10 to the zeros. 10 to the 0, of course, is just 1. So that's the number of ones. The 0 represents the number of tens. The 4 is the number of hundreds. And the 1 is the number of thousands. If you add all of these up, right, they get you back to the original number. You probably learned this, I don't know, back in 5th grade or something like that. And even at the time, you kind of look at this and say, well, yeah, okay, so what? This way of thinking as a number as being made up of added powers of the base is going to be an essential step in taking a number in a different base and putting it back into base 10. So finally, you see what I did here. I took this number and I kind of split it up into this table form. And to convert from other bases back into base 10, we're going to kind of work this process backwards. All right, so let's look, for example, here. I have this number. It's a binary number. It's in base 2. Of course, in base 2, the only possible digits are 0 and 1. And you can see that, right, in my example here. Those are the only digits used. So what I want to do here is I want to write this. I want to write the equivalent base 10 number. And the way I'm going to do that is, like I said, I'm going to work my process from the previous slide backwards. Right? So I'm going to start by writing out my number here over the representative powers of 2. Right? The number in the first, the right-hand position, represents 2 to the zeros. The number in the second position represents 2 to the firsts, and so on. All right, so now all I'm going to do to convert this into a base 10 number is I'm going to write this out. This is 1 times 2 to the fourth plus 1 times 2 to the third plus 0 times 2 squared plus 1 times 2 to the first plus 0 times 2 to the 0. And now it's just an arithmetic problem. You get your calculator out and let's see, 2 to the fourth, that is 16 plus 8. 2 squared is 0, but there's 0 of them. Plus 2 to the first is just 1. It's just 2. Plus, again, another 0 here. You add all of these numbers up, and you get our final answer. This binary number is equal to 26 in base 10. All right, so we've got another example here, and I'd like you, if you're watching this, to pause the slide, to pause the presentation. Take a second, try to do this on your own, see what you come up with. And then you can start the presentation up again and see how I come up with a solution. All right, so I'm going to use the same approach. Right, I've written out, I've got 3 digits in my number, so I've written out 3 powers of 8. So I'm going to write my individual digits in here. That's the 3, the 1, and the 7. And now I'm going to add them up. I have 3 8 squareds. I have 1 8 to the first, and 7 8 to the zeros. All right, so let's see. 8 squared is 64, so this is 3 times 64 plus 1 times 8 plus 7. And here's where you have to be careful. I see weird things happen here when students start doing this. Sometimes they'll write that 8 to the 0 as 8. Sometimes I'll see them, they'll write that 8 to the 0 as 0. Right? Remember, anything to the 0 power is just 1. All right, so let's see, what does this turn out to? 3 times 4 is 12. Carry the 1. This is 192 plus 8 plus 7. So my final answer is 207. All right, so that's one way, right? All right, so that's one way. Now, suppose we want to go the other way. Now I have a base 10 number, that's the 412, and I want to rewrite this in base 5. Okay, well, there's two approaches to this kind of question. The first one really is kind of applying that same sort of table-based system that I had before. I want to break this number apart into powers of 5. All right, so how can we do that? Well, the first step is a little bit trial and error. I need to work out some bases of 5. So let's see. 5 to the 0 is 1. 5 squared is 25. 5 to the third is 125. And 5 to the fourth is 625. And that's where I'm going to stop. Right, I'm going to stop here because my powers of 5 became bigger than my original number. Right, so I know there are no 5 to the fourths, if you will, in 412. So here's going to be our next step. We're actually going to kind of apply the division algorithm. Right, I'm going to divide. Let's cross this 5 to the fourth out because we're not going to use this one. I'm going to take my biggest number, that's the 125, and divide that into 412. Right, so let's see, that's 3 is 375. And we very carefully do some subtraction. This becomes 7. This was 10, carry the 1 again, so this is going to be 3. All right, so what does this tell me? This tells me that 412 is equal to 3 times 125 plus 37. That's what our division algorithm says. All right, so now I'm going to kind of cross 5 to the third off because we're done with that one. And I'm going to keep working my way down. I'm going to take my next power of 10, and I realize here I left one out. I left out 5 to the first. Right, let's slip 5 in there. We're going to need him in a minute. So let's take 25 and divide that into 37. See, that goes in once. Put 25 down here, subtract, and we get 12. All right, so 37, I'm going to rewrite this again. This is 3 times 125 plus 37, which is 1 times 25 plus 12. All right, now let's cross off the 5 squared. We don't need it anymore. And let's do this again. 5 divided into 12. It's 2. And we're going to subtract. So 12, and see what I'm doing? I'm going to keep going. This is 3 times 125 plus 1 times 25 plus 2 times 5 plus 2. And here I'm actually done. There's really no point in dividing by 1, right? Dividing by 5 to the 0. So I'm just going to put the 1 there on the end. Now look, let's rewrite this a little bit. I'm going to rewrite all of those things I divided by as powers of 5. So this is 3 times 5 to the third plus 1 times 5 squared plus 2 times 5 to the first plus 2 times 5 to the 0. And notice how this looks just like our base 10 numbers did, right? It's decreasing powers of 5. So in base 5, this number is 3, 1, 2, 2. Right? I just picked out the numbers for each of my powers of 5. Now, we're not done though. Look, I know this is a fine point, but it's an important one and students often leave it off. What I have written here is not true yet, because what I've said so far is 412 is equal to 3,122. Those are both both base 10 numbers, and that is obviously not a true base 10 statement. So what I have to do to finish this off, I have to specify the base on my final result. Okay, so that's one method, right? And that's not bad. It's a little mechanical. You have to spend some time doing a little long division, but that's not too bad. There's another method that I think is a little quicker, right? Especially when we're dealing with a big number like 214. There's 2 to the 14th, 2 to the 6th, 2 to the 8th. I think we're up at a pretty big number. But before we get to a power of 2 that is greater than 214. So here's the second method for doing this, and this is actually the one I usually use personally. It's based on just repeated division by 2. So I'm going to say 214, start with the original base 10 number, divided by 2 is 107 with a remainder of 0. Then you just keep doing this. Take the number that was left, right, the 107. 107 divided by 2 is 53 with a remainder of 1, and I'm just going to keep going. 53 divided by 2 is 26, remainder 1. 26 divided by 2 is 13, remainder 0. 13 divided, whoops, not divided by 2, by 0. Divided by 2 is 6, remainder 1. 6 divided by 2. 3 divided by 2. Let's see, 1, remainder 1. And finally, 1 divided by 2 is 0, the remainder of 1. This is how you know when to stop. When you get to 0. When you get to 0, you're finished, and you can go on to the next step. Now here, this is why I like this method. Now I've got my answer. All you have to do is read the remainders backwards. 214 decimal is equal to 110,10110 base 2. Right? To me, this is quicker. I don't know, maybe you prefer the other method. Either one is fine. Right? You're going to get the same answer no matter which one of these you use. So I have one more number system that I want to talk about here, and it's the so-called hexadecimal system. Hexadecimal is Greek for 16. So this is a base 16 system. And we immediately, hopefully, first thing that kind of occurs to you is that we're running into a little trouble with the digits. We have 9 in our base 10 system. And when we're talking about bases less than 9, that was fine. We just chopped it off. If we want to talk about base 5, then we just took the first 5 digits, 0 through 4, and ran with them. Now we need to add instead of remove. So all we're going to do is we're just going to use letters. Right? I'm going to use A, B, C, and so on up through F. I want you to think about what these represent now. A represents 10. B represents 11. C is 12. And you got to be careful here. F is just 15. Not 16. Remember, in our base 10 system, the biggest digit is 9. That's one less than the base, right? Because we always start our counting here at 0. All right, so let's see. So I have a specific example here. I want to convert F3B6 base 16 into a decimal number. So I'm going to use the same process I've been using. I'm going to write out, first, we have a 4-digit number here. So I'm going to write out all the first 4 powers of 16. And then I'm going to write my digits in, F, 3, B, and 6. And to get my final result, I'm going to multiply each digit by its respective power of 16. So let's see, but I actually want to do this with their decimal numbers. So F is, let's see, A, B, C, D, E, F. That's the last hexadecimal digit. So this will be 15 times 16 to the third plus 3 times 16 squared plus, all right, B, A, B, that's going to be 11 times 16 to the first plus 6 times 16 to the 0. All right, now really you got to get your calculator out. 16 to the third is 4,096. 16 squared is 256. 16 to the first is 16. 16 to the 0 is 1. So let's see if you keep working this out. This is 61,440 plus 760. Excuse me, that's not a 13. That should just be a 3. That's 768 plus 176 plus 6. Add all those together, you get our final answer. 65,798. Base 10. All right, so now what? Now that you've got the basic idea here, right, how to go back and forth between these two types of numbers. In the next lecture, what we're going to do is we're going to kind of take the next obvious step, and we're going to look at how we can do arithmetic, right? Addition, subtraction, multiplication, our basic arithmetic operations using numbers in different bases, and it's going to follow, the very same pattern that you've already learned for doing all of those operations in base 10.